So let's still down with a question like this, in which you have two identical objects that have the identical charges Q1 and Q2. So mass of object 1, if we call this object 1 and this object 2, is the same as mass of object 2 as well. Charge of object 1 is the same as charge of object 2. And then they are hanged into a string with length L, each of them, into the wall. The string is in a string that doesn't allow the charges to move from one to the other charge, to the other object, and then therefore that means that the string is a non-conducting string. Now, what we will find on this question is we will find what is the tension on the string, what is the electrostatic force that the string is or the charges are experiencing, and what is the magnitude of those charges which actually are equal to each other. And for simplicity, I'm just calling it Q. So every time that we have a question that is asking us in regards to forces, the very first thing that we do is we find or we draw the free body diagram. In class, I did the free body diagram of object 1. Now on this video, I will do the free body diagram of object 2 to tell you that this is the same thing. So you can pick one of them, it doesn't really matter. So the object of our interest, which is the object 2, is represented by a dot, and then we have the force of gravity of object 2. And let's put a value for the masses so that it is clear for you, 2.5 grams. And then the other force that the object is experiencing is tension, which the rule for tension is going along the string starting from the object. And the third force that the charge 2 is experiencing is the electrostatic force, which we know now based on the general law of charges is a repulsion, since the two charges 1 and 2 are equal to each other. Now, the key on this is that the charges are in equilibrium. So being in equilibrium, meaning that the sum of all the forces, which is force net, is equal to 0. So in this case will be force of gravity plus tension plus electrostatic force is equal to 0. This is what being in equilibrium means. Now, since this is a 2D situation, so it's with a certain angle, theta here, which just so that you are used to having a number, will be, I will say, 12 degrees. Since this is 2D situation, then what we will do is we will add using components. So we'll go horizontal and vertical, force of gravity, tension, electrostatic force, and the sum of all those forces is equal to 0 because the object is in equilibrium. So the horizontal component of force of gravity will be 0. The vertical component will be negative 2.5, that is the mass of the object, times 10 to the power of negative 3 to convert it into kilograms, times 9.81. So this will be negative 0.0245525. The horizontal component of the tension will be this vector here. So this will be the horizontal component of the tension, horizontal, and this will be the vertical component of the tension. So the horizontal component of the tension, since it is opposite to the given angle, will be negative because it's going in the west direction, whatever is the tension, which we will find, times sine 12 degrees. And for the vertical component is positive t times cosine 12 degrees. Now the horizontal component of electrostatic force is positive Fe, and the vertical component of it is equal to 0. Now we don't know on this relationship what is the magnitude of the tension and what is the magnitude of the electrostatic force. However, let's draw and figure out what are the equations that we are getting from the horizontal component, and this will be negative t sine 12 degrees plus Fe is equal to 0. And from the vertical component, we will have negative 0.024525 plus p times cosine 12 degrees is equal to 0. As you see here on the horizontal equation, we have two unknown. So we don't start from there. But when we take a look at the vertical, then we have only one unknown, which is the tension. So this will be 0.024525 divided by cosine 12 degrees. And this divided by cosine 12 degrees. Make sure that the mode of your calculator is on degrees. So then the tension will be 0.0251 newtons. And the direction is identified by the free body diagram. Now we take this value of tension, and we substitute it into the horizontal equation. So now we will have negative t, which is 0.0251 times sine 12 degrees is plus Fe equals to 0, which means that Fe, or the electrostatic force, is times sine 12 will be 0.0521 newtons. We can write those values in the scientific notation form, and if we do so, then we will have the tension will be 2.51 times 10 to the power of negative 2 newtons, and electrostatic force will be 5.5. Actually, there is another 0 here. 5.21 times 10 to the power of negative 3 newtons. So they are asking you to write it into the form A dot BC times 10 to the power of negative D. For tension, you will record it as A dot BC times 10 to the power of negative D will be 2, 5, 1, and 2, while for the electrostatic force in the form A dot BC times 10 to the power of negative D will be 5, 2, 1, and 3. However, the question is asking further to figure out what is the charges between the two objects, knowing that L is, let's suppose, 1.50 meters. Now, what do you have here on this case is two options to find. First, electrostatic force is Q squared, because the two charges are equal to each other, over R squared. But we don't know what is R squared. We do know now what is the electrostatic force is 5.21 times 10 to the power of negative 3, but we don't know what R is. So let's figure out what R is with that addition that what do you have is is that length, or the length of the those two lengths of the isosceles triangle is, as I said, addition to is 1.50, I think, meters, 1.50 meters. And now each of those angles we said that is 12 degrees, or the whole thing is 24 degrees. And what we are looking is this R, which is between charge 1 and charge 2. You have two options to find it. The first one is to use cosine law. So you can go R squared is equal to L squared plus L squared minus 2 times L, which is L squared again, times cosine 24 degrees. And then you don't even have to square root it, because in the relationship it's R squared. Or the second option is to use the right angle triangle. Right angle triangle. So on the right angle triangle, you are looking for half of the distance, knowing that L is, in our case, 1.50, and the angle here is 12 degrees. Any of the equations that you will use, or ways that you will use to solve for R, will be fine. In the class, I used the sine here, or the right angle triangle, and now I will use cosine. So R squared will be 1.50 squared plus 1.50 squared minus 2 times 1.50 times 1.50, which I said is 1.50 squared, times cosine 24 degrees. Do not forget that the mode of your calculator has to be on degrees, and R squared will be 0.389 meters squared. So now in the equation that we have here, which is the Coulomb's law, we can find out that charge squared is equal to R squared times electrostatic force over Coulomb's constant. So, or Q is the square root of R squared times electrostatic force over Coulomb's constant. In our case, what we will have is 0.389, that is R squared, times the electrostatic force was 5.21. So 5.21 times 10 to the power of -3 over 8.99 times 10 to the power of 9. From entering this in your calculator, you will find that the charges are 4.75 times 10 to the power of -7 coulombs, or 475 nanocoulombs. So this is the question that deals with the equilibrium of the two charges being connected, tied with non-conducting wire.